So hello all. Up till now we have seen divisors of 0. By divisors of 0 what I mean is, though A and B both are non-zero elements, if their product happens to be 0, we say that A and B are divisors of 0. And here we have observed in case of Z6 that 2, 3 and 4, they are divisors of 0, whereas 1 and 5, they are not 0 divisors, because though if they multiply non-zero element, product is not a 0 over there. So I feel you are quite familiar now with the concept of divisors of 0. Now let us proceed. This theorem also we have done. If you have ring Zn, then in ring Zn, divisors of 0 are those elements which are not relatively prime to n. So as you saw in case of Z6, 2 and 3 were not 2 and 6 were not relatively prime, 3 and 6 were not relatively prime, 4 and 6 not relatively prime, still 2, 3 and 4, all of them, they are divisors of 0. And if we see in case of 5, 5 and 6 are relatively prime, so 5 is not a 0 divisor. 1 and 6 are relatively prime, 1 is not a 0 divisor. So I hope it underlines the fact that precisely those non-zero elements are 0 divisors which are not relatively prime to n. So let us now proceed. Let us use this concept, and we know in case of prime, in case of ZP, every member of ZP will be prime to P. So it has no 0 divisors. Now, yesterday we stopped with the cancellation laws. Let us talk about cancellation law now. What is cancellation law basically? Yes, anyone? If suppose I have A into B equal to A into C, then we cancel A on the left side. It's a cancellation law. We call it as a left cancellation law. And if at all we are having A to the right side and cancel it, we call it as right cancellation law. As you know, in case of ring, as far as multiplication is concerned, there are restrictions. In a ring, what surely we have as far as multiplication is concerned, multiplication is binary, multiplication is associative, and lastly, multiplication distributes over addition only. Here we are cancelling the things, etc. Means to cancel means we are multiplying by the inverse, and we don't insist in a ring that every element must be unit element and so on. These things are not there. That is why the question of whether cancellation laws hold or do not hold occurs. So in this case, what we mean to say, there are two parts of this statement. Cancellation laws hold in a ring, and second part is R has no 0 divisors. So these are equivalent statements. Cancellation laws hold, then R has no 0 divisors. And if R has no 0 divisors, then cancellation laws will not hold. This we mean to say. Now let us go with the proof. We suppose that the cancellation laws hold. This is our first part. And we want to show that R has no 0 divisor. No 0 divisor means though A and B are non-zero, their product must be equal to 0. Apart from being non-zero, their product is 0, we'll call them as 0 divisor. So you can suppose there are A into B equal to 0. What we mean to say is either A is 0 or B is 0. If both are non-zero, then there will be 0 divisors. Our assumption is the cancellation laws hold. And we started with A into B is equal to 0. Now, if A is non-zero, then what will happen? I can say that A into B is equal to A into 0, because 0 multiplied by any number is 0, that we know. So A into B is equal to A into 0. So what this will mean? Cancellation laws are holding. Cancellation laws are true. So A gets cancelled on the left side and you got automatically B equal to 0. Now B is 0 means what? If I multiply by a 0, answer is 0. So it cannot be called as 0 divisor. So neither A is a 0 divisor and B is itself 0. So no question. Same way, if you put restriction that B is not a 0, then you'll come to the result that A becomes 0. Why? Because of the cancellation laws. And therefore, A and B are not 0 divisors. So what you proved? If the cancellation laws hold, then R has no 0 divisors. Followed the thing? Okay, only one response. All right, I would like to go once again. Once again, I would like to go back. Okay. See, what is your assumption? Your assumption is cancellation laws hold. And you want to show that R has no 0 divisors. So obviously, you will take product to be 0. Wherever there is product 0, we will see over there and we will try to see whether the multiplicants, any of them, is a 0. If none of them is a 0, then we'll conclude that there is a 0 divisor. As I have shown that 2 3 is a 6 in Z6. 2 bar into 3 bar, you know, is 6 bar, meaning 0. Neither 2 is a 0 nor 3 is a 0. Still the product is 0. Do you agree? Yes. So apart from having non-zero numbers, their product is 0, means they are 0 divisors. Now in this case, we try to observe what happens, because I mean to say, I want to find out the multiplicants. The answer is 0, I know. But with what multiplicants I got the answer 0? Is it necessarily a 0 number? Because you know, if I multiply 2 bar into 0 bar, what will be the answer? If you multiply 2 0, certainly the answer is a 0. There is no question. But apart from having both non-zeros, the product happens to be 0. In that case, we call them as 0 divisors. That is our definition. Okay. Now I would like to go back to my statement. I once again reassert that cancellation laws hold. Cancellation laws hold. Okay. Now I'm assuming that A is non-zero. Okay. If A is non-zero, then what will happen? Because the cancellation laws hold, what we get is A into B is equal to 0, and I know 0 can be written as A into 0 again. Do you agree with my statement? Can I write 0 as A into 0? Sure. And now let me cancel. Let me use my cancellation law, because that is the hypothesis. So I cancelled it. What is your result? You directly got B equal to 0. So can I call A as a 0 divisor? No, because A multiplied to a 0 will always produce a 0. So I can't say in this case that A is a 0 divisor. Same way, If I start with assumption that B is non-zero, what is our target? We want to see whether A happens to be non-zero. I started with B not 0. Now A into B is 0, I know. But 0 can be written as 0 into B. This is for my convenience. I'm taking 0 into B. I can write it as B into 0 also. But this is for my convenience because I know cancellation laws hold. Now I can cancel B. And what is the output? A is
A equal
0.
to 0.
So I got this at 0. So now B cannot be a 0 divisor. Because if B multiplies to a 0, answer will be certainly 0. So there is no other go. There is no other case. And that is why I come to the conclusion that R has no 0 divisors. Followed now? Okay, still two thumbs only. Okay, third. Hope you have followed it. Okay. Now, this is if and only if. So we have to prove the equivalence. So let me go ahead with the reverse way. I suppose that R has no 0 divisors. And I want to show that the cancellation law holds. So how should I start? R has no 0 divisors means I have to start with A is not 0. This is the converse part. So shall I change my ink? Okay, I would like to change my ink. See here. Neither A is 0 nor B is 0. But product AB is 0. What is the meaning of this? What is the meaning of this? A is not 0, B is not 0, still the product AB is 0, means A and B are 0 divisors. Is it so? But what we want to assume, R has no 0 divisors. Okay. What I mean by this, unless any of them is a 0, the product will never be 0. If you want the product to be 0, one of the multiplicands must be 0. This is our meaning. And what we want to prove? We want to prove that cancellation laws hold. So let us start. We assume that AB is equal to AC because we want to reach to the cancellation law. Do you agree? I want to show that cancellation laws hold. So I start with AB is equal to AC. What else we can do with this? So I can bring all the terms to the same side as usual. AB minus AC. What you'll suggest me after this step? I hope you'll suggest me to take A common. Can I take it so? Yes, because multiplication distributes over addition. Subtraction is nothing but addition of additive inverse. Okay, so A times B minus A. And what is the result? Because I have carried AC to that side. So what must be the result to the right side? It must be 0. So I got A multiplied by something equal to 0. I repeat, A multiplied by something is 0. And my assumption was A is non-zero. If A is non-zero and R has no 0 divisors, what this indicates? A must multiply to a 0, then and then only you will get a 0. Do you agree? Because R has no 0 divisors, it is not possible that two non-zero numbers multiplied together produce a 0. This is not possible. So A should multiply to 0 and then only the result will be 0. That's why B minus C must be certainly 0. B minus C must be certainly 0. And if B minus C happens to be 0 means what? B must be equal to C. Did you get my statement? B is equal to C. Means actually from AB is equal to AC you started and you reach to B is equal to C. Means as good as you cancelled A on both sides. Do you agree? Okay. Okay. So once again, I would like to explain this to you. Once again, let us go with it. See, you want to prove that cancellation laws hold. So you have to start with this kind of thing. That is damn sure. Now, what you will say about this? A is non-zero. Why for? Because A is a common thing that you are taking and you want to prove that there are no zero divisors. Just now we have seen the definition. Two non-zero numbers multiplied together produce a zero. Means R has zero divisors. Here I want to show that R has no zero divisors. Means by a non-zero number, if I multiply to a non-zero number, answer comes out to be zero, means R will have zero divisor. Here we want to talk about the reverse way. So what we'll do, one number I have selected, A not 0. Now I can just solve this as AB minus AC is equal to 0. I feel all of you agree with this. By distributive law, I can say A common inside B minus C. The reason will be by distributivity. So this is left distributive law, isn't it? I must mention that it is left distributive law. Now what happens? A is not 0 is mentioned over here and the product is being 0, and moreover it is told that R has no zero divisors. So as R has no zero divisors, what will happen? The second number must be certainly 0 because the product is 0. I know first number is not a 0. So second number has to be 0. That's it. Followed? If R has no zero divisors, the second number must be certainly 0. What this indicates? B must be equal to C. From where you started? From AB is equal to AC you started. Where you reached? B is equal to C. Means you have cancelled A. This is the straightforward meaning of this. And what it means? Left cancellation laws hold. Same way you can go with right cancellation law. BA is equal to CA. Suppose A is not 0, then only we will proceed. Again, A is taken common, you'll use right distributive law, etc., etc. And I hope you can reach to the result. Followed now?
Yes, madam.
Okay, okay, okay. That's fine. Now, I would like to proceed ahead. So, for the time being, I would like to skip this. All right. And now we are reaching to the definition of integral domain, which is quite important for us. What is an integral domain? So many definitions up till now we have seen, and we have to concentrate on each of them. So integral domain is a commutative ring with unity 1 not equal to 0 and containing no divisors of 0. I repeat, it's a commutative ring. So basically it's a ring. Multiplication is commutative. Multiplicative identity is there and it has no 0 divisors. Such a ring we call as integral domain. I repeat, ring is commutative, contains unity, and there are no 0 divisors, then it is an integral domain. So what do you think? Is Z6 an integral domain? Is Z6 an integral domain? Is multiplication commutative there in Z6? Either say yes or say no. I would like to go over here. This is our Z6. It is in front of you. Is the multiplication commutative? Is it symmetric about the diagonal? Yes, it is. Multiplication is commutative. Does it contain unity? Yes, unity is there. Okay. Does it have 0 divisors? Are there 0 divisors?
Yes.
Yes, 2, 3, 4, there are 0 divisors. So will it be an integral domain then? Will it be an integral domain?
Yes. Yes.
What is an integral domain? It should not contain 0 divisors.
No.
No, Z6 is not an integral domain. Got it? Z6 is not an integral domain because it contains divisors of 0. Okay. My question to you is Z7 an integral domain? Does it contain 0 divisors? Is Z5 an integral domain?
Yes.
Is Z11 an integral domain? Did you observe what I wrote over here?
Odd integers.
Not odd, not odd, not odd.
Prime.
Yes,
Not
I'm just taking primes. Yes, I'm taking primes. And just now you have seen if P is prime, then ZP has no divisors of 0. Got it? If P is prime, ZP has no divisors of 0, meaning if P is prime, ZP is an integral domain. Got it? So Z7, Z5, Z11, Z13, all of them, they are integral domains. But Z6 is not an integral domain. If I ask you, what about Z8? What about Z8? So 8 is not a prime. So Z8 is not integral domain. What about Z12?
Not integral domain.
Yes, it is not an integral domain. Okay. And you can see green actually we use for yes, saying yes. but here I have reversed the thing. है ना? Green color I have used for those which are not integral domains, and red color I have used for those which are integral domains. So keep this in mind. These are integral domains. Okay. I feel you got me. I would like to move ahead then. So Z is an integral domain. Z itself, Z is the set of integers, but it has no zero divisors. So if I say I take any two positive, I take any two integers with me. A is an integer, B is an integer, and I say the product is zero. So will A and B be non-zero always? Is it possible with non-zero integers? Can
No.
you, yes, can you tell me any two non-zero integers whose product is zero? It is not possible, not possible. And that is why Z is an integral domain. At the same time, ZP for prime P is also an integral domain. So keep this in mind always. Okay. Now, one more thing I want to underline. Please concentrate on this fact. If suppose you have two rings, if suppose you have two rings, R is a ring, S is a ring, and you take the cross product R cross S. You know, R cross S is also a ring. I have taken two non-zero rings, R and S. R cross S surely is a ring, but it cannot be an integral domain. It cannot be an integral domain. What is not an integral domain? Direct product is not an integral domain. Why? Because you may have members like this, R comma 0. Suppose I take 10 comma 0. Okay. And here I may have 0 comma 7. What is the product? We multiply them individually. And 10 zeros are will be 0. 7 zeros are will be 0. Answer is a 0. Apart from having non-zero entries, the product will be 0. So direct product of two non-zero rings cannot be an integral domain. Followed me? Direct product of two non-zero rings cannot be an integral domain. Have you understood the fact? Okay. Okay. Why it is not so? Because we multiply coordinate wise, I mean component wise. And if one of the components is non-zero, we say the pair or triplet, whatever, is non-zero. So though one entry is 0, the other may not be 0. So I will not call this as a 0 element. So it's a non-zero, and I multiplied two non-zero elements, producing output as a 0. So always be cautious about determining an integral domain. Feel you're satisfied. Okay, then I proceed ahead. Z2 is an integral domain. How? How Z2 is an integral domain? Can anybody explain me? Can Z2 be an integral domain? Yes.
Yes, ma'am.
Why?
Non-zero numbers are like multiplication zero.
No. Z2, Z3, Z5, Z7, all of them, they are integral domains. Z11, Z13. Yes, what is the reason?
Prime numbers.
Yes, they are primes. And just now we have said ZP is always an integral domain whenever P is prime. Z2 obviously will be an integral domain because it is 2s prime. Followed me? Now what are the members of Z2?
0, 1.
0 and 1.
Zero.
Only 2 entries are there. And last time we have visited this M2 of Z2, set of all 2 by 2 matrices with only 2 entries, 0 and 1. So the statement is show that although Z2 is an integral domain, the matrix ring has divisors of 0. Means matrix ring M2Z2 is not an integral domain. And you can watch here. I've taken 1 0 0 0 multiplied to 0 0 1 0. Still the answer is 0. The product is 0. So product of two non-zero matrices, I'm getting a 0 matrix. So this M2Z2 is not an integral domain. Followed it? So you should have this statement M2Z2 is not an integral domain.
Madam, how to write M to Z2?
I'll tell you. Okay, so keep this in mind. M2Z2 is not an integral domain. It's very important. And I would like to go back to your question. No, it is not here. So last time I dealt with the set of matrices, 2 by 2 matrices with 1 and 0 as the entries. I hope you know this. In our previous video, you'll find the set of matrices containing 1 0 and 0 1. What were the entries? I hope you remember them. Just a minute. So M2 of Z2. So it contained matrices containing all zeros, all ones, three ones, 1 0, three ones, 1 0. I hope you remember this. Do you?
There are 11 elements, no?
Yes. There are in all, I think, 12 entries. Is it so? There are.
11.
I'm not getting 11. Yes. So there will be 12 entries.
12. Madam, how to directly find out the women's entries?
Actually, you can go with the concept of probability, possible ways, possible outcomes. Once you fill one place, yeah, with either 1 or 0, likewise. Place wise, you can go with that. Okay. So what I have done, I have fixed my first place, first row, first column entry by 1, and then I'm just trying to fill up ones elsewhere. That is the strategy. Likewise. So last time we have done so. I hope you can go through. Okay. So here again, you'll find matrices whose product, they are themselves non-zero, but the product happens to be zero. Okay. Because this is not ordinary product. Keep this in mind. Keep this in mind. 1 plus 1 is what? Yes, come on. 1 plus 1 is a 0 here. Keep this in mind. So what will happen if I multiply these two matrices? 1, 1 and this 1, 1. What is going to happen? Product of these two matrices. I selected these two matrices. So 1 into 1 is 1 plus 1 into 1 is 1. I got this at 0. Then I go over here 1 into 0, 1 into 0, this is 0. Next 0 into 1, 0 into, so 0. And last one 0. So what do you find? Apart from having non-zero matrices, the product is 0 here. So you observe that the product of these two matrices is a zero matrix. Apart from having them to be non-zero, their product happens to be 0, and that is why this M2Z2 is no more an integral domain. Is this fine? Okay. So hope the concept of integral domain is somewhat now clear to you. Now I would like to go to this theorem. We want to show that every field is an integral domain. Every field is an integral domain. So what do you mean by a field? Field is a commutative ring with unity where every non-zero element has an inverse. Every non-zero element has an inverse. So what you observe here, we selected F to be a field. A and B are members of this field, and we suppose that A is not 0. Because to show an integral domain means there are no zero divisors. This is our target. So we assume that A is non-zero. Now if product AB is 0, because F is a field, every non-zero element is a unit element. It has inverse. So 1 by A exists. I pre-multiply by 1 by A. So what do I get? 1 by A into A is 1. So I got this to be 1 into B. Right side is 1 by A times 0, so it is 0. So what we got? B is 0. So if you have product AB at 0 and A is non-zero, surely you got B to be 0. So it has no zero divisors, and that is why it is an integral domain. So let us once again see what is an, how to prove it. You said F is a field. So what are the requirements of a field? Commutativity for multiplication is a must. What next? It should be a ring with unity. So unity is there. And what next? Every element is a unit element, invertible element. Every non-zero element is a unit element. That is the requirement. Now, we want to show that it is an integral domain. So for an integral domain, we start with product AB equal to 0. And let us suppose that A is non-zero. If A is non-zero, then inverse of A will exist. 1 by A will exist. So we multiply both sides by 1 by A. Now, what we observe here, so 1 by A times AB, we can use associativity. So by associativity, this will be 1 by A into A and multiplied by B here. To this side, any number that multiplies to 0, answer is a 0. Now what next we know? 1 by A into A is 1. So we got this to be 1 into B. And right side is 0. So directly we got that B is 0. So if B is 0 and A is non-zero, what this means? By a non-zero number, if I multiply to 0, then only I am getting 0. Means A is not a zero divisor. And if there are no zero divisors and it's a commutative ring with unity, we call it as an integral domain. So field is necessarily an integral domain. Okay, field is an integral domain. Okay, every field is an integral domain. Hope so. Understood the concept? Got it? Okay. Now we can picturize it. What do you observe over here? So these are all rings. Now we can see that a ring with unity is shown over here. Some rings with unity may be commutative, so it is intersecting here. Now all rings with unity and that are commutative may be integral domain, but every field is an integral domain. So field is the innermost part. So what do you observe? Field is subset of all. Field is in the intersection of all. Then comes integral domain. Integral domain is a ring with unity. Integral domain is a commutative ring. So we have to keep this figure in mind. Okay, this explains the relation of all those ring structures. Followed it? Okay. So with this only I would like to stop.